Okay, you guys can hear me? All good? Okay. Alright, so today we'll start, close the door. Is that one going? Okay, so today we'll start with unclonable encryption. So this is a very interesting primitive. Yeah, so I'm mostly going to be almost entirely going to follow this paper, and it gives us a it gives us two results. It tells you what kind of schemes can satisfy unclonable encryption. Cannot satisfy unclonable encryption, and it gives you a scheme that does satisfy unclonable encryption. It does it in what is called the random oracle model. So I will explain that as we go on, what that model is. It doesn't do it in the plain model. That is still an open question. Okay, so there's lots of open questions in this area, and they're very hard, but you never know, right? One of you might actually solve it. So what is unclonable encryption? So unclonable encryption is yeah, so let's just start from the beginning. I was going to tell you the abstract, but then it doesn't make sense to tell you the abstract at this point. Okay, so unclonable encryption is capturing the idea that if there is some ciphertext C that is given to, say, some party A, okay, it shouldn't be the case that A can give it to both B and C, okay, such that they can recover the message. They can both recover the message. Okay, so we'll formalize what this means, but that's the idea. So so C is say this is an encryption of some message M. So it shouldn't be that S prime, S and S prime should not both be M. Okay, but we know already that this notion of security is not enough, right? Because this is asking you to produce the entire message. It could be that half messages are produced by both and so on. So this notion will not be adequate. So we'll do it through indistinguishability and so on. Okay, but that's kind of the flavor of what we're going to do. Okay, so let's start more. So this is like a very, very broad sketch of what the property is. So let's look at it properly now. So unclonable encryption is, so it is a one-time. Actually, I'm not fully sure yet what they mean by one time. So I'm going to write one time, and then when we go to the proofs, I guess I'll figure out and I'll tell you. So it's a one-time secure encryption scheme okay, with quantum ciphertexts. Satisfying the following guarantee. So satisfying essentially what I said here is that no adversary given a ciphertext which we're going to model as a quantum state, as we have been doing, modeled as a quantum state. Can produce two possibly entangled states, okay, such that both of them encode some information about the original message. So here I said that they should not both be able to produce M, but really what we want is that both should not be able to produce S that has some information about him. Okay, like we did when we discussed semantic security and all these things, right? That you shouldn't be able to compute even a function of M, not data message. Okay, so that's the intuition. And how we formalize this is using the following splitting game. Okay, so I don't know if the dots are visible. Okay, good. And this is formalized. Oh, I should mention I added the third assignment. I'll add the fourth one. If the assignments are too heavy or too light is good. If it's too heavy, tell me. They should be relatively simple. And from so the lectures which were about review and so on, I have put proper exercises. The ones which are about covering the paper, it's not very clear what kind of exercises I can put because either they're research questions or they're just simple. So a big part of the assignment would just be to look at I don't know how many of you are crediting first of all. There's probably 2 or 3, right? Okay. So for you guys, a big part of the assignment for the parts which are based on actual material would just be to produce class notes. So half of that would just be to produce class notes, just to make sure that you're actually following. So nothing very. If you think it's simple, you can just roughly argue what has happened. But for the formal part, the informal part you don't have to write. The formal, the proofs, when the proofs appear, that would be like a big part of the assignment. Okay, I'm just saying it because you can then take notes in class if you think that's saving your time. Okay, good. So back to the construction. So unclonable encryption. So this is the idea that we want to formalize. So this is formalized by the using the following splitting game. Okay. So what is the game? The game here is as follows. Okay. So you consider. By the way, all of this is going to be informal until I actually tell you that we are in the formal phase of this. Okay. So we're going to consider a splitting adversary. So what a splitting adversary is basically 3 quantum algorithms, A, B, and C, okay, which are essentially of that form. Okay. So first, so A receives an encryption MB, M sub B, of 2 messages, one of 2 messages. Okay, it's either M0 or M1. And then A then outputs a bipartite state to B and C. Okay. So you give an encryption of M0 or M1. This is A. A sends a bipartite state. Oh shoot, I messed up. I actually made a very big mistake here because, okay, nobody pointed it out. Okay, what is completely dumb about this construction? This definition. Okay, I claim this definition is very easily satisfied as long as the ABC are computationally bounded.
It's possible to just output click garbage. Like they may not decrypt back. Yeah.
They may not. No, you want to prove that there doesn't exist ABC that would violate it. Yeah. Come on, this is how you define security, right? This is what we discussed. So security is like you have a game and you define a class of adversaries and you want to say the scheme is secure if no adversary in that class can break it. Right?
C is a quantum ciphertext. Can't cloning theorem in this.
Yeah, we will come to it. So the reason is that.
Like C can be same as A, and you can just output garbage in B.
Yeah. So.
That is fine.
Yeah, we want to say that this security can be broken. Like you can construct a scheme such that even, what you're saying is that, okay, there's one class of adversary that doesn't violate the security. I want you to prove that there isn't any adversary that will be able to break it. So, okay, let me phrase the question more clearly. Can you think of a scheme, and I'm telling you that you can, it's very simple. Can you think of a scheme which you already studied, which will satisfy the property that no BNC can simultaneously decrypt the message.
B and C can communicate.
They can't. Yeah, of course. Otherwise, it's just one adversary. Yeah. I'm missing something very, very straight. It doesn't even have to be a quantum state. What I'm saying is very dumb. Okay, so
What is the correctness definition?
that you should be able to decrypt if you have the secret key. Yeah, that's I'm not writing that. I'm just writing the unclonable property. I'm assuming that the encryption scheme is, as we discussed before, like it satisfies whatever indistinguishability.
Previous scheme, right? Like that we read. So unless they are together, they will not get message.
Yeah, even if they are together, right? I missed a very key thing in this definition. Any scheme which is a secure encryption ensures that neither B nor C can decrypt it, right? Even a classical scheme will satisfy this property.
Like, but with the private key, it can be.
Yeah. That I haven't given them anything. That's the thing I messed up, right? I didn't give them the key. I just said that you give them the ciphertext. Of course, nothing will happen. So to make it non-trivial, you have to give them something, right? So the key thing is that even if you give them the secret key, like Jayan said, even if you give them the secret key, it shouldn't be that both of them can recover. Okay, so now it becomes non-trivial because, okay? Yeah, so you have to spot my stupid mistakes like this.
So is it like somehow secret sharing over ciphertext? Like you're sharing ciphertext with both of them such that like none of them can encrypt individually.
Yeah, but it should still be an encryption scheme, right? Because it should be that, one of them, because you don't have any control over A. So in secret sharing, you would need A to produce the correct, but A is an adversary, so they can just send the whole thing to one party and then they can recover it. So it's not. Okay, you appreciate the definition, right? It's sort of. Uttam bhai, you look confused. Is everything?
What does A do?
It's an adversary. It's a QPT adversary, and the objective is to for both of them to learn the message.
What does A send to B and C?
It's up to A, whatever they want. It's part of the strategy. So it's a tripartite adversary. So the adversary has three parts: A, B, and C.
So if I think of encoding like our previous protocol, so I produce S theta state and string X. So unless both of them know X and theta both, they cannot produce them.
No, but A is an adversary as well, right?
But-
It has the complete ciphertext.
Yeah, so for example, he has two parameters for encoding theta and X.
What are you trying to do? That's the question. What kind of ABC are you trying to produce? Are you trying to produce? You're saying A behaves a certain way such that BC can't do something. Then, like Jan said, A is not trusted. Right? There's no reason why A would do what you're telling him to do.
Okay. So what is this then? So what does B and C get so that even with the secret key they cannot get masses?
Yeah, that's the whole thing. Like you want to come up with a scheme such that regardless of what A sends, it shouldn't be that both B and C can recover the message.
Okay. So this is the definition. I was thinking of protocol itself.
Yeah. This is the security requirement that we're thinking. So it's very informal.
Even if you do this, like let's say there are few messages which you lose some information but not critical information, still the messages, you will get the message but you will not get the whole message.
That's even harder to formalize, right? Like, I mean, you might as well formalize that you get no information about the message. No, not satisfied. Say it again. What were you saying?
I'm saying
Maybe I didn't understand.
You get S and S dash,
Uh-huh.
but they are not same. But you will get the whole objective of the message, but they are not same.
Right. Exactly. That's why I'm saying that this definition is weak. You're right. They shouldn't be able to compute anything which is a function of the message either. Like we formalized earlier, right? Like exactly. Just as we did earlier, right? We said that what if you learn whether the amount is, I don't know, if say M is the salary, you get a estimate of how big the salary is without knowing the actual salary.
Yeah, even like parity.
Or you could get a parity, something like this, right?
Is it that when you give both B and C the secret key, like depending on who uses it first to like get the message, say if like B uses the secret key first, then like maybe some state will collapse and C like won't be able to use it.
Right. Normally, the secret key here is classical.
So how do you determine like which one of the two will like?
Yeah, so you require that both shouldn't be able to do it simultaneously. One of them might be able to do it, but both should not be able to do it. So that's what you're trying to
One
formulate.
does it, then the other one cannot. Is it?
No, you just say that the joint probability that they would win should not be more than half, because so at least one of them has to make a random guess, something like that. Because it can always be that A just sends C to one party, right?
There is no precise notion of time. I mean, you just say that A sends, so A hits in fast, and BC will happen simultaneously.
Yeah, they're space-like separated, so they can do whatever. Yeah, so B and C are sequentially dependent on A, but B and C themselves can output whenever. We just require that eventually they will produce some outputs, and then we're going to make some statements about the outputs.
So what is uncloneable here? What does uncloneable mean?
You tell me.
So they cannot clone message, encoding of message.
Yeah, let's suppose C is classical, right? Then no classical encryption scheme will satisfy this property, right? Because you can always have, right? Why? Because you can always have this adversary A send C to both B and C, right? And they both get the secret key, so they can both recover the message.
Yeah, he can send the full encoding.
You can send the entire thing. But if it's quantum, then it's not clear how you would do
Then
it.
he cannot copy the C so that it
Yeah, but it may be that you still, B learns half the message, C learns half the message, but that's not enough, right? What we want is that only one.
definition.
Yeah. I mean, this definition is a little bit crazy, but like we want a proper notion of security, right? Like we said in
Yeah, we
the
want
last time.
reproducibility of
Yeah. So that's what we formalize. Okay. So let's see how they formalize it in the paper. So in the paper they formalize it as follows. So there's B, okay, and then there's C, and oh shoot, yeah, I didn't write the full statement here. Sorry. So since the full state B and C, A outputs a bipartite state, sends it to B and C, okay, who also get, this is where I realized I messed up. So who also get the secret key, the classical decryption key. Decryption key and secret key, I think, because we only did. Yeah, so when we think of public key, we call it a decryption and encryption keys. Decryption key as an input, and the output B sub capital B and B capital C respectively. Okay. So in terms of the drawing, so A gets an encryption of either M0 or M1, sends a bipartite state BC, can be entangled potentially, and you have a classical description. Classical decryption key. Decryption key. SK. Okay, both parties receive this, and they have to output a bit B, which says B sub capital B, B sub capital C. Okay, and the winning condition is what? And they win if little b is B sub capital B, which is the same as B sub capital BC, B sub capital C. Okay, so
Why do we want to do this?
good question. I skipped the application part. I can tell you the application part. So first of all, it's one of those things that you cannot do classically and you can do quantumly, and it's very cool that you cannot produce copies of the ciphertext. Okay, so classically you could have stored it. So one very very simple example is the following. So suppose that, which is the case, we don't have good quantum computers, okay, and people are using classical encryption. And what you do is you keep a database, like so suppose you're listening in on some embassies communicating, and you keep a database of all the emails being exchanged. And eventually, suppose they're using some encryption scheme that you think a quantum computer can break eventually. So you keep the copy, and then eventually when the quantum computer is ready, you use it and you break it. If you were using unclonable encryption, this is not possible, right? Because you cannot keep a copy of the ciphertext.
So classically, if I want to think that, like you said, that if A produces two ciphertexts, then he can send separately. So it's like perfect correlations between A and B and A and C. Can I think like that?
Yeah, let me. I didn't actually write the full definition. Let me quickly write the. So let me write one observation actually. Okay, so brilliant. Okay, so note the following. Right, this we already said. A could just send the entire ciphertext. Entire ciphertext to B, okay, who can output B little b equals B with probability 1, okay. And so the security condition must necessarily be, okay, so we require that there does not exist any splitting adversary that wins. Yeah, okay, so NB1, NB2 is that, so there exists a splitting adversary that wins with probability. Okay, so using NB1, we know that we can win with probability at least half, right? Because okay, so the security requirement is that there does not exist a splitting adversary that wins with probability negligibly greater than half. Okay, and so the definition would be that an encryption scheme satisfies unclonable indistinguishability. So that's the word they use for this indistinguishability game. If it, meaning this requirement, holds for all splitting adversaries. Okay. So now coming back to your question about correlations. So yeah, so we can make it such that either B is able to figure out which message was encrypted, or C is able to figure it out, but it cannot be that both are able to do it somehow. Yep.
Yeah. So like I have one question. So like see, so since like ciphertext is classical, right?
Mm-hmm.
Is the ciphertext classical? Okay.
But then you can't satisfy the definition, right?
Yeah, like that is what I was thinking.
Yeah, that's what we were saying right there. That I kind of glossed over it, but the point is that you could, like, it's always good to first try to give a classical construction, right? Because the quantum is not a very feasible technology yet. So this is one of those things you cannot achieve classically, because an adversary can always just send the same message to both, and so there's no way you can.
Why do you need two messages and not only one?
Indistinguishability, remember you were there for the cryptography review, right? So over there, remember we were talking about semantic security, that you should not be able to learn anything about the message. There were these, there was a probability that you get the message M, right? We said that security, so this is information theoretic, okay? So it's like for the one-time pad. And we were saying that we wanted to be such that the probability that you get the message M should not be affected by the fact that you got some specific ciphertext, okay? And then later we found that this condition is essentially the same as the following, that you have some ciphertext and you encrypted some message M0, and this is the same as getting a ciphertext given that the message was M1. Okay, it's one of the exercises in the assignments as well, you'll see. So this is sort of the semantic security style definition, that you're saying that you had some prior distribution about what messages will be sent, and after seeing the ciphertext, your distribution over the messages doesn't change. Okay, and then you can show just by playing around with the probabilities for at least for the one-time pad that this is equivalent, right? Is it for the one-time? I think no, it's just in general equivalent for information theoretic security, that whether your message being encrypted was M0 or the message being encrypted was M1, the probability that a certain ciphertext shows up is the same. Okay, which is what we're capturing here. So we are using this definition because it's easier to work with. So we're using the computational analog of that. So computational analog is regardless of whether I encrypted M0 or M1, you shouldn't be able to tell which one was encrypted. That's the indistinguishability game. And now we're doing it with two parties.
So in the second one, like when like the probability of C equals to C, like given M is equals to M1, so aren't we assuming that like the probability distribution of a message is like uniform?
Where are we assuming that?
So I'm thinking of that thing in terms of like Bayes theorem. So you will have your like probability of M is equals to M0 or M is equals to M1 in the denominator, and you just like flip the probabilities there in the numerator.
But Bayes theorem doesn't require M to be uniform.
Yeah, where does Bayes theorem say anything about uniformity?
I mean, how do I do that? I'll like tell that after the class.
Yeah, it's an exercise. I mean, you can do it yourself. You can prove it. It's not difficult. It should be
So
okay.
if I introduce a D, like A sends to BCD,
A sends to BCD.
so there are three parties it sends, and I want to satisfy uncloneable with this indistinguishability, then still everything will remain the same, right? The definition that no splitting adversary will win with probability half plus maybe.
If you have three, like, so then the other two also have to make the right guess. So I don't know, you might have to look at it a bit more carefully. Maybe they always make the same guess.
Guess with half probability.
Yeah, but all of them getting it right would probably be, yeah, maybe it's half. Because if they make independent guesses, then it would be half times half, because like they both have to get it. It's just the probability that, you know,
No, but if I look
BA equals BB equals BC. So one of them will be able to get it right, the other two having gotten it right.
but you
Because
will not require that BB equal to BC, right?
That depends on
You individually require that BB should be B and BC should be B. So they will guess.
oh, already. Yeah, you want all of them to be yeah. I mean, it's okay. The two, you can't split it in two. I think you can prove that you can't split it in three either. Like all of these things are corollaries. I guess you can formalize it.
Yeah, I was just looking at the definition.
Yeah. I suppose that. Yeah, I haven't thought about it, but it should be, because you know it's almost like indistinguishability, right? Like you could say, oh, why am I only doing M0, M1? I should do M0, M1, M2, M3, M4. But the point is, if you can't distinguish any two, then you can't distinguish anything. So I think it'll be similar here as well. If you can't split it into two, you can't split it
It
into.
will be trivial probably, but the definition will it remain the same? I think.
Yeah, one can think about it. I don't want to say anything wrong, but yeah, I haven't thought about it. But it should be something along those lines that, yeah, that the trivial attack would be that, yeah. So the trivial attack would be that one party can guess, one party can guess with probability 1, and the others guess with at most half probability. So it probably would be half plus the negligible probability. Yeah. Because there's no reason why they should make independent guesses that have to match. They could all make the same guess. But could they?
No, I mean, why
Yeah,
should
they could.
require-
Yeah, A could make the guess for them and then just tell them. Yeah.
But they are not communicating, right? So they have to make their own guesses.
No, but A can make a guess and send it to all of them. I'm just trying to construct an adversary that wins with at least probability half, and it's okay. Let's do it afterwards. Let's not get distracted. It's okay. Okay. Any other questions about, well, clarifying, not extending, just clarifying what we're discussing? Okay, good. Okay, so this is fine. Now we're going to make like a very nice elementary but nonetheless a nice observation, which is, let's call it 1.1, 1.2. Yeah. Okay. Do you guys see this immediately? So semantic security is like standard indistinguishability, right? Okay. So how do you prove a statement like this? You normally do it with a contrapositive. Okay, so you assume that, suppose you have an adversary that breaks semantic security, then you can also break unclonable indistinguishability. Okay, so it's a stronger notion. So how does it work? So negation of semantic security implies negation of unclonable encryption. Okay, why is that? So suppose you do have an adversary, okay, that breaks on this semantic security. Okay, what does that mean? That means that, you know, there's an adversary A that from the encryption of M0, M1 can figure out whether M0 was encrypted or M1 was encrypted with non-trivial bias, right? That's what the standard indistinguishability game is, right? Given encryption of M0, M1, you shouldn't be able to tell which one was encrypted. So if semantic security is not followed, so you have an adversary that can predict. So let's just write it. A semantic adversary allows A. So we have this three-parted thing. So A is going to be able to decrypt. So it allows A to compute B sub A. Okay. So it can guess B sub A, which corresponds to B, and then sends B sub A to both B and C. Okay. B and C output. B defined as BA and BC defined as BA. Okay. And now, because we know that the semantic adversary gets BA with, half plus non-negligible, right? B and C also output BB, BC identical, which are correct with half plus non-negligible, which violates the half plus negligible requirement. Okay, so that's the second note. So that's the definition. That is what it is. Now to look at some applications very quickly.
So in this thing, adversary A was itself breaking the semantic security, right?
Yeah. So that's the construction that's one way to do it. Maybe there are other ways of doing it, but because we're assuming that the ciphertext itself is potentially quantum. In fact, it has to be, right? Otherwise, it's not. So you have to have A do something. Okay. So now we look at some applications. Applications of unclonable encryption. Okay. So first of all, it implies something we haven't yet studied. We'll likely do it.
Pedagogically, so this concept of unclonable encryption, was it with this paper or it was before there in the literature?
Pedagogically, you mean chronologically?
Sorry, chronologically.
Chronologically, no, there was I'll tell you the history as well a little bit in a moment. It was introduced by Broadbent and Lloyd.
But that was too very early.
Huh?
That was still in 2020, I guess.
Yeah, these are very recent things, yeah.
It was not before. So how
I mean,
come up with these constructions that they want this kind of things?
Oh yeah, so maybe you can the applications, you can think of it in many ways. One is that unclonability is like quantum money has been one of the things, right, that people have been thinking about from like very early on.
Yes.
But they really formalized it in terms of encryptions relatively late, unfortunately or fortunately, whichever way. So there were lots of ideas about clonable, unclonable, and also like the machinery, I guess, didn't exist, right? We didn't know how to do verification and all of this. So like using computational assumptions to build cryptography is relatively new. Quantum crypto. Like earlier, people were mostly thinking about information theoretic security, and so on. So yeah, that move that even if you make computational assumptions, there are things that you can do quantumly that you cannot do classically. That is relatively new. Okay. So one of the applications is that it actually implies private key quantum money. Which intuitively one can see, right? Like you can, you can't clone it, so you sort of can use it for money. But we'll likely look at quantum money in another set of lectures. The next one, which I mentioned in passing, was that it prevents storage attacks. Okay, so storage attacks are where you are trying to malicious entities are stealing ciphertext to decrypt later. Okay, when the security key is compromised. So either when the key is compromised or the computers get better, whatever. I shouldn't say the computers get better because the security that we looked at assumes that the computational assumptions continue to hold. So I misspoke. Here is just saying when the security key gets leaked. Unlike the case of certified deletion where things were information theoretic. So here they're not. Okay. And then finally,
Here, to implement this scheme, you would need a quantum computer. And you're saying that now we have bad quantum computers, so that when they get better, you could do the storage attack. But then to do this, you need a good quantum computer.
No, I misspoke. So earlier I said something about the evolution of quantum computers. That was not the right statement because I was thinking of certified deletion where security is information theoretic. So even if you're unbounded, you could not potentially break the security. Here, it's more that you assume everyone has quantum computers, but you're just waiting for the key to get compromised. So yeah, that's a good point. Sorry, I misspoke. Is it okay? You look a bit confused. Yeah.
But if the key gets compromised, so can't the adversary just decrypt the message first, then send it classically to the other, like to the other adversaries, like the NC?
Yeah, of course. If you have the point is that you're listening in on some communication, right? So usually you're thinking that there are two servers, and you're listening in, and you're sending one back, and one you're keeping. So it's that kind of a setting that we're thinking of. Yeah. But of course, like you could just keep the whole thing, right, and then you'll get detected.
Right.
So I guess you don't want to do that. So you want to send one
Right.
through one. Okay. At least that's how I understood it. Maybe they meant something else, but I think that's what they meant. And then you can do what is called copy protection. This is very cool stuff, which I also don't know anything about, but I guess I'll learn in the coming weeks and tell you. The idea is that you have a program, and it should not be possible for you to copy the program and run it somewhere else. So you should only one party should be able to run the program.
Then the
Okay.
program is like the message or the algorithm?
It's an algorithm, so that's why it's different. Otherwise, like you could just get it from encryption. So you not only do you want an encryption of a message that can be decrypted, you want a program that you can run on inputs that you want, but the program should somehow be quantum, so you cannot give it to someone else. Only one party can run the program, something like that. We'll formalize it later, but the intuition is just this, that you shouldn't be able to copyright. Like classically, you shouldn't be able to pirate the software, basically. So a restricted class of functions with computational guarantees. So yeah, these are not information theoretic things. I guess there are no-go theorems. Okay, so this is where unclonable encryption sort of shows up. Okay, and now we look at some prior works, which is what Uttam was asking. So we look at a little bit of the background, and then because we'll build on one of the schemes, the previous schemes that doesn't satisfy the full notion that we want, and then we'll see how to do it. Okay. Prior works. Okay. So previous work showed a weaker property, showed a construction satisfying a weaker property. Construction. Okay, what was the weaker property? So they showed a weaker property called unclonability. Okay. This is similar to what I was saying in the beginning before I gave the unclonable indistinguishability. Okay, so instead of indistinguishability, it's just called unclonability. And what is it? What does it say? It's the same. So it's the same as unclonable indistinguishability. Except A, they assume that coming to what you were saying, they assume the message. Okay. Assume messages M0 or the message M is sampled uniformly. And B and C are expected to guess entirely, or in its entirety. I'm just being lazy, so messed up English, but okay. Okay, so it's the same, except that they're making some assumption about the distribution over messages, which is not good, right? We said that you could have some priors already on what the distribution would be. So this is not a realistic scheme. And second is that they expect you to produce the entire message M, unlike the first case. Okay. And as a consequence, so the first thing is this is less useful, right, in practice because you can't use it in cryptographic contexts. And second is that it does not satisfy semantic security. Right, so we saw that indistinguishability, unclonable indistinguishability implies semantic security, right? This definition does not even imply semantic security. Okay. And that's that's relatively easy to see, right? Because maybe I leave it as a small exercise, but you can imagine that you have an encryption where you, like, say if it's lambda bits, M has lambda bits, and the first bit you just leave in the clear. Okay, so it could be that the BNC cannot guess M in its entirety, but they can still get the first bit. So that's not semantically secure. Okay, so you can always. So this is not strong enough. Okay, good. Okay. And at the time when this paper was written, it wasn't clear whether, actually it's still not clear whether we can do it in the plain model, but at that point it wasn't even clear whether you can do it at all in any kind of model. So the main question was, whether unclonable, indistinguishability exists. So any scheme satisfying unclonable encryption exists. Okay, so that was the key question. Okay, so that's one part of the thing. The other thing is about copy protection. So we'll look at what the results are in just a moment. Okay, this is just setting up the stage for what was known before these guys started their work. Yeah, I think let's do it. I'm just trying to decide whether I want to cover copy protection later or if I should just do unclonable encryption.
They use some construction from that copy protection.
It doesn't look like that. I think they use the construction from unclonable encryption to build copy protection, but I don't think.
Copy protection or the NDR paper?
They use coset states, yeah. Well, but that's independently introduced. Okay. Maybe let me give you the thing. I think it's just good to know. Even if you don't cover it, at least you'll know what copy protection is when you study it next time. Okay, so here's the story. Looking at copy protection for point functions. Okay. So another very interesting primitive is this copy protection, right? So what does it do? Informally, okay, it's a compiler. That converts any program into a quantum state such that the following two properties hold. So the first property is that the original functionality is maintained, right? So original functionality is maintained. And the second property is that, the unclonable property. So the following holds. What is the requirement? It's going to be similar in terms of the splitting adversary. So let's see how they formalize that. Okay. Okay, so a splitting adversary Let's see if I have it drawn. No, I don't. Okay. ABC, right? So it first receives okay, so first A receives as input. So let's draw it here. So A receives as input a copy protected state, right, as input, a copy protected state that can be used to compute F. Okay, so let's say this is some kind of a, so let's say compile acting on F. Okay, this is what you give to the adversary A, and then A outputs a bipartite state, right, as before, bipartite state to B and C. Okay, so there's B and C. They get the answer from this. Okay, and the security is both B and C should not be able to compute. Should not be able to simultaneously compute. Oi, oi, bless you. Compute F. Okay. Okay, so that's sort of the, so yeah, they should not both be able to compute F or whatever.
When you say compute F, does that mean like for a input X, F of X, they cannot output F of X? Or?
Yeah, they cannot both output compute F on some input. They don't formalize whether the inputs are the same or not. I guess we'll see it in the formal definition later. But at the moment, it's just capturing the intuitive notion that both of them should not be able to simultaneously use the function in any useful way. Yeah? Okay, good. So let's see. So what do we know about these things? Again.
This uncloneable thing and the compile F.
Oh, because you can run it on many inputs, right? It's so if I give you a cipher text, well, first of all, I should make sure I understand your question. So your question is, how is it different from unclonable encryption, right? So in unclonable encryption, you're not guaranteed anything other than the fact that you can recover the initial message, right? But this is much more versatile, right? It's saying that you have an arbitrary function, polytime potentially, and after you compile it, you preserve the functionality. Right. So
the functionality is one thing. Other than that,
oh, that's the main thing. Yeah. The definition might be slightly different. I don't know how they formalize it, but yeah.
In this case, B and C do not get any extra information, right? Like previously, they were getting the cipher key. In this case, there's nothing like that.
That is. Yeah, actually, I don't know. They didn't write it in the thing. That is a good point. Let's see. So the thing is that when they say the original functionality is maintained, I guess, yeah, that is probably the more important difference that I didn't catch. Assuming I'm not messing up, it seems that when they say the original functionality is maintained, it looks like you can do it without the secret key, right? It doesn't look like you're forced to have a secret key. So somehow, yeah, it does seem to be something more special.
Since this is a point function,
Where's the point function?
copy protection for point function.
That's just the heading, yeah. Point function hasn't arrived, yeah. This is just the definition, yeah. I was going to say about point functions, yeah.
What's the point function?
I'll define it, yeah.
Define it. I'll ask it.
Okay. Yeah, no, that's just the header. Good. Yeah, so to answer your question, Uttam, one of the things, unless I'm wrong, that he said is that we're not giving secret keys to B and C. So it seems different in that regard, and then there's this extra functionality.
Does that imply A also can compute?
Yeah, that probably will always be the case, right? A can compute and give the answer to, but then that doesn't sound right. How would you?
Secret key business, I mean, compile it, I don't know what it does, right?
Yeah,
And
yeah.
it sends something to B and C. It might send secret key, whatever you want to call it. There is no notion of such. The goal is to be able to compute it. And it's not even saying that you send the secret key or not.
Yeah, maybe the idea is that you can't compute it on different inputs, maybe something like this. That maybe you're given, yeah, I don't know. Let's see how it happens, how they properly formalize it. Okay, good. So I guess we'll have to do the formal thing. Now you've piqued my curiosity as well. Okay, so prior work said what? So prior work was done by AL21, which said that so copy protection is impossible. Impossible for general unclonable. Why am I writing unclonable? Sorry, unlearnable. Okay, so first of all, I should define what a learnable function is. A learnable function is that you query it a few times and you learn the entire description of the function. So, for example, if you have a constant function, right? So obviously you can clone it, right? Because it's a constant function. You can tell B and C that it's constant, so they can just output it. So first of all, you have to restrict to something that is unlearnable, right, for the definition to even make sense. And even then, there are results that show that you cannot do it for arbitrary unlearnable functions.
Learn the entire function.
Yeah, so you query it a few, like for example, if it's a linear, if it's outputting a dot product, so it's hiding some y, and every time you.
It's constant for like all the inputs except for one.
Yeah, that's a point function. Yeah, learnable meaning efficiently learnable in the sense that you make poly many queries and then you can learn it. Yeah. Of course, otherwise, if you query the whole truth table, you can learn anything, right? Yeah. You can do
So
it.
this is even stronger. I mean, even if you have conditions on it, still it's not possible.
Yeah. So that's why this result is non-trivial, right? So they have to prove it that, you might imagine that if you cannot learn a function by querying it poly many times, then at least those functions you should be able to copy protect. Right? Because certainly if you can query and learn, then this you should not be able to copy protect, because A can then just query and learn the function and then send the description to B and C. Right? Okay, so this was the first result. So here what they look at is, so what about a simpler class of functions? So what about simpler classes of functions? Okay, and this is what?
So, like in the Simon's problem, so we just want to tell whether it's constant or what is it?
Yeah, you're finding the period, for example.
Yes. So is it learnable function?
Yeah.
Because with quantum mechanics.
Yeah, with quantum it's learnable. Yeah. Because yeah.
So it will happen. For example, many what is not called like not entire functions.
I didn't understand the question. It will happen, not entire functions.
So I mean, there will be. It's impossible for general unlearnable functions.
Yeah. Let's make the set, right? Okay. So suppose this is the set of all functions. This is unlearnable, right? And then there's certainly like a small little set which is like point functions. So they showed.
Functions are unlearnable.
Yeah, they're a subset of unlearnable functions, because a point function, I didn't define it yet, but it's just a delta function. So it outputs one. It's like a search question, right? Like there's only one marked element, everything else is unmarked, and you have to figure which is the marked element. So obviously, if you have no prior information, then you have to query it, right, at essentially all the points in general, in the worst case. So this is like a very small subset of unlearnable functions, and what they're claiming is that you cannot. Yeah, so in general, if you're given an unlearnable function, then they show that, so basically the statement is that there would exist at least some unlearnable functions that you cannot copy protect, and they show that there is at least this small little class of functions that you can copy protect. Yeah, I'm going to write it now. Yeah. Okay, so the example point functions. So there are two kinds of point functions. Okay, so what they call a single bit output point function is just a delta function. Okay, this is just a delta function. So f of y on any input is just, or on input x is just delta xy. Okay, which is 1 if x equals y, 0 otherwise. Okay, so that's one. The other one is a string output or a multi-bit output. So the multi-bit output one is exactly the same except same as single bit except outputs a large string. Okay, so when it doesn't match, I guess it will give you one string, and when it does match, it will give you some other string, something like that. I'm not sure why that helps exactly, but apparently it makes a difference. Okay. Okay. So this is what we had. Okay, so what did prior works show? So another prior work, actually there's two of them. So there's CMP 20 and then AK 21. Yeah, I did not fix the issue of remembering the names of the people, so I'm going to ask you to look at the paper. Sorry. Oh, I think I know one of them. This is Kaladanshla and Paramba, and AK. K could be Dakshata, but okay. Okay, so what they do is they construct copy protection. For either multi-bit point functions or with single bit point functions. With constant security. Like how we want the security to be, whatever, half plus negligible in that sense. So it's instead of half plus negligible, it's half plus a constant. So that's not ideal. Okay. So what these guys do is they extend it. Yeah. So this point function, you can think of it as multi-bit and a single bit. So they do it for the single bit case. That's all they say about it. That is annoying. Okay. So I guess we'll have to wait a little bit. So the question they try to address here is, does copy protection for a single bit exist? With optimal security exist? Okay. So as you can see, this is a pretty insane area to work on, right? Because we know very little. We only know for point functions, and that also this paper shows how you do it for 1-bit output point functions.
And optimal security, that you want to get rid of constant
So So for multi-bit, I guess they had proper security. For single bit, they couldn't do it, and these guys closed that that last step by using techniques from unclonable encryption. Okay. Alrighty. So now we're going to look at why it's hard to build unclonable encryption. All of this is just overview, okay? We'll actually do the... This is the introduction, actually. I think the tech overview will start a bit later. Okay, so this is what are the difficulties in building unclonable encryption. Indistinguishability, challenges. Okay. So remember we had like these two notions of unclonable encryption, right? Like there was the unclonable indistinguishability, and then there was the simpler one, which was unclonability itself, right? Which was that you have to output the entire message, right? So one might think that one can go from one property to the other because okay, so you might think unclonability can be used to construct unclonable indistinguishability. Okay. Why is that? Because there's what is called a search to decision reduction. I don't know if you've heard of these things. The point is that you're trying to extract the entire message in the definition that we said for unclonability. So that's like a search problem. You have to find the entire message okay. While a decision problem is, can you distinguish yes or no? It's a single bit. And often what one can do is one can show that if you can distinguish, you can also, if you have an algorithm that can do the distinguishing, then you can construct an algorithm that can do the search. Is that the direction I want to say?
Other direction sounds
Search to decision reductions. So you want to reduce your search problem into a decision problem. Right.
Like if you have an n-bit string, the decision problem could be is the first bit 0, is the second bit 0.
Yeah, you can check bit by bit.
Yeah, so the problem is that if there's like a unique answer, then I think it's easier. But if there is no unique answer, then it's a little bit harder. So there are some issues that arise. I also actually clearly don't know much about this. But let me just say what the paper said. So what the paper says is the following. So one might think you can do this because this one is a search problem, and this is a decision problem. And one could hope that one can apply search to decision reductions. Search to reductions. But it turns out that this approach doesn't actually work. And why it doesn't work is because apparently of like superposition messes things up in the classical arguments, and there are multiple parties that are involved in the process. Okay, because normally you have like a single distinguisher or whatever you're trying to construct. Here there are multiple parties, so that makes things a bit more complicated. So that is the first one. Here are some other approaches that one might use to build. All of this is just to get some intuition. Okay, we will look at the actual construction and proof in a bit, but oh no, I only have 5 minutes. No, I have 10 minutes, right? It's 12:30. Okay, good. So, okay, so what are some of the approaches that fail? So approaches that fail. Okay, so the first one is, so let's see, why is it tricky to use usual crypto primitives? Okay, so by now we are a little bit familiar with things, right? Like we know, okay, I don't know if you've done the assignments are new, but we looked at encryptions, right? We saw the one-time pad. We did not look at the pseudo-random generator. I think these things are in the assignment, but you'll see. Okay, so consider this construction. Okay, I'll explain whatever is needed. So consider this. So suppose the gen procedure produces, let's write it here. So gen 1 to the lambda samples k uniformly at random and returns k. Okay. And the encryption scheme does the following. It encrypts the message m by sampling 0, 1 to the lambda, and it returns r comma prf of k comma r XOR m. Okay, so I don't know if you guys saw the lectures. I had posted the construction for a CPA secure encryption scheme. Okay, and this was the construction essentially. Okay, so for those of you who may have forgotten, a PRF is just it's indistinguishable from a random function as long as the key is sampled uniformly. Okay, so if r and this r is sampled uniformly, right, by the encryption scheme. Oh, sorry, the key k is sampled uniformly by the generation procedure, and then this encryption scheme is going to sample an r, and it will use this r as an input to the PRF, and this PRF will produce a random string. Okay, so why this scheme has CPA security is because if you encrypt the same message again, okay, it will sample a new r, okay, and you'll get a new ciphertext. So you cannot run those attacks that we had earlier, that you encrypt the same message, like if you wanted to distinguish M0 and M1, right? If you had an encryption oracle, if the encryptions were the same, so if M0 was always encrypted to C0 and M1 was always encrypted to C1, then if you have access to the encryption oracle, if the challenge ciphertext is C, you can just encrypt M0 and M1 yourself and check whether it matches C. So deterministic schemes cannot possibly satisfy this. So that's why you have to do all the work. Okay. Good. So this is the scheme that they consider. Okay. And then even if you have something very simple, right? The question is what goes wrong when you're trying to analyze a game like this. Okay. So in the security game, the key k, right, is revealed to both B and C. Okay, so clearly they can both learn, right? Clearly both can learn okay. So a simple scheme like this is not going to work because any kind of primitive that we use from cryptography is usually assuming that there is some secret key, and the point is that B and C both get access to the secret key towards the end. So it's really non-trivial how you would even use any kind of cryptography, because all of cryptography is essentially based on keeping the secret key secret, right? So that's one approach that doesn't work. The other approach that doesn't work is as follows. okay, which is about security reductions. So let's see what example they give here. And the question is, which adversary among B and C should be used to break the underlying game, right? The security game. Because we've always had only one party, right, that's trying to break things. Now there are two parties, and we don't know which one of them you're going to use to give the. Okay, so example. If you use B to break the game, so if B is used, A could have simply handed over the ciphertext to C. The ciphertext C to adversary C, right? And so now information theoretically B cannot break the security, right, or whatever you were trying to do. Correct? So suppose you decided that, okay, I'll use B to break the security game. It's always possible that A didn't give B any information about the ciphertext. It gave all the information to C. So then obviously information theoretically it's not possible for B to break the game. So that's not going to work. Okay. And then things get a little bit more complicated. So what happens, what if A sends a superposition? Entire ciphertext, entire C to B, and entire C to. So what if you do this in a superposition? With coherently with some amplitude you send the entire ciphertext to party B, and with some amplitude you send it to party C. How do you do the reduction? Okay. Okay, and then C is the issue of extending unclonable indistinguishability from 1-bit messages to multi-bit messages. Okay. Yeah, maybe I'll add this as an assignment. So we know that, here if once you construct the security for a 1-bit message, it's relatively easy, right, to extend it to m-bit messages. What you do is you just extend the thing, and then you can do a bit-by-bit hybrid argument or something along those lines. So it's usually not very difficult to do it. Okay. So classically, 1-bit to multi-bit is through a hybrid. Hybrid argument. Okay. So this fails here, at least directly. Okay. How does it fail? So suppose, here's a good example. So suppose a 2-bit message, m equals m1, m2. So this means concatenation, okay? Did I get something wrong?
Can you explain that part again? What if A cannot, it sends a superposition entirely C?
Yeah, I think I messed up the sentence. What did I write?
Sending the register or like, sending something?
Sorry. No. I think I messed up. Okay. Oh shoot, that was a different sentence. Sorry, your question is about point 1 or point 2?
Point 2.
Oh, sorry, I just wrote it in a bad way. Yeah, so here it was, what if A sends a superposition of the entire ciphertext C to B? So it was sending us a state, right? So this was A, right? And it was sending B and C, right? Sending to B and C some state, correct? So suppose the state psi was psi BC, okay? And suppose the state is so suppose it received some ciphertext C, okay? So what if he sends this? So he sends superposition, for the moment equal superposition, so sends C to party B and junk to C plus junk to party C and C to party I. Right? So now how do you know, how would you argue that the adversary breaks the security and so on? So it gets more complicated. Yeah. Thank you for the question. Okay, so this fails here. If you try to apply directly this 1 bit to multi-bit, so suppose there's a 2-bit message, okay, M1, M2. Okay, so this is encrypted as row 1, row 2. So row 1 is encryption of M1. This is encryption of M2. Okay. Then it's not hard to check that this scheme is. So this scheme. So assume these are unclonable encryptions. Row 1, row 2 are unclonable encryptions. Then the composite will not be an unclonable encryption scheme. Okay, so the scheme is not unclonably indistinguishable. And I'll leave it as an exercise for the moment, and I'll tell you next time, because we're out of time, I think, and you guys have other classes and so on as well. Okay, so we'll pause there. Oh, feedback.